Hey everyone in calculus. The next really big thing that we're going to be learning about is going to be called the mean value theorem. It's another one of the AP tests, greatest hits. So, you're guaranteed to see this on the AP test. So we're going to study it just a little bit here today. And let's get started by looking at our zombie situation of the day. So here we got our zombies. And we've got a consistent characteristic of zombies is their need to ingest the brain matter of the living. Zombies will give chase to living characters in works of fiction and with an unrelenting drive. In older classical depictions of zombies have poor locomotive skills. They're not very well coordinated, really. And it is the sheer number of zombies and their unstoppable drive that makes these undead creatures a force of nature. So, just speaking zombie talk, this is actually the kind of zombie that I prefer. I think when the zombies are those fast variety zombies, it kind of loses a little something. This whole force of nature thing is something that I really enjoy about the zombie trope. So let's go with our calculus. We've got the mean value theorem. So if you have a function that's continuous on a closed interval, in other words, it goes all the way to the edge of your interval, and it's differentiable on the interior, so not necessarily differentiable at the endpoints, but differentiable everywhere in between, there is a place C where f prime of C is equal to f of b minus f of a over b minus a. And let's unpack what this really is. F is a y coordinate. So we have a difference of y coordinates on top of a difference of x coordinates. This is a delta y over a delta x. And when you do that, hopefully every algebra student will recognize that as a slope. So what we're saying is that the derivative is equal to the slope of that line that connects the endpoints together. So let's do some kind of a drawing here. Well, here's a function, for example. We can call the left side A and the right side B. And the line that connects those two in green here, the slope of this line is just the y coordinate at B minus the y coordinate at A over B minus A, which is exactly what we have here, f of B minus f of A over B minus A. That explains the right side of this. Now what about the left side? What is that? Well, that is the derivative. And so what this really says is that someplace on this curve, we have somewhere between A and B is a place where the tangent line has the same slope as this is what we would call a secant line. So let's try to figure out where that place is. Now if I duplicate this secant line and I kind of slide it up and down, pretty soon I figure out right over here, this place has the exact same slope as the secant line. The tangent line right there has the same slope as the secant line. And as long as these conditions are met, as long as we have continuous on the closed interval, differentiable on the open interval, then we're going to guarantee that this has to be true at least one time, possibly more. So that's what our mean value theorem says to us. There has to be a place where the slope of the tangent line is equal to the slope of the secant line. So let's move on a little bit and see what we have here. We've got a problem. We've got a zombie running, not really running because it's a zombie, but at a bunker, running toward a bunker filled with people. A bunker is a shelter, let's just say a shelter. And the distance from the bunker, the zombie's distance from the bunker is modeled by this equation. Y equals the root of 25 minus t minus 5 quantity squared. t seconds after it starts running. So that's the distance equation. So we're going to use the mean value theorem to explain why the zombie's speed must equal 1 foot per second sometime in the first 5 seconds, 0 to 5. So this phrase right here, the zombie speed must be equal to 1 foot per second. That's something that always signals to me that we're looking at a mean value theorem or something like a mean value theorem. We'll see a few more before we're done here in calculus. So first thing we're going to do, this in our brain says that the derivative has to be the slope of the secant line. So the first thing we're going to do is figure out, this equation here says that the derivative is equal to, and this over here, this is y at 5. This is y at 5 minus y at 0 over 5 minus 0. Okay, well that is just the slope of the secant line, yb minus ya over b minus a. And we get that that's equal to 1. So when you compress this all down, this says that at some place, the derivative dy dx has to equal 1. So we just got to figure out when that's going to happen. And so to do that, of course, what is the equation for dy dx? Actually, I'm getting ahead of myself. Since f of b minus f of a over b minus a equals 1, and y is a continuous differentiable function from 0 to 5, the zombie speed has to equal 1 someplace between 0 and 5. So this is kind of the way that mean value theorem or the mean value theorem works. Okay. So let's move on. Let's see what we have here. Some definitions. Okay, if we know that x2 is bigger than x1, we're going to have the definition of increasing right now. I bet you didn't think you'd need a definition of increasing. But increasing says that if f of x1 is less than f of x2, which is the same thing as saying f of x2 minus f of x1 is greater than 0, that means that the function is said to be increasing. So let's remember that little bit right there. We've got, this is the part that says, this is the definition of increasing. Okay, f of x2 minus f of x1 is greater than 0. And then we can say the same thing about decreasing. Decreasing happens when f of x1 is greater than f of x2. The y-coordinate on the left is greater than the y-coordinate on the right, which simplifies, or not really simplifies, but that's the same thing as saying f of x2 minus f of x1 is less than 0. When we take those definitions together, we can come up with one of the most important concepts in calculus. So what is that really important concept in calculus? Let's see. This is a little bit of a proof here. We're going to start off with the fact that f is decreasing on an interval I. In other words, x1 is less than x2, which in another way of saying is x2 minus x1 is greater than 0. Okay, that's true. And if we're saying that f is decreasing, then from up here, we know that this is true. F of x2 minus f of x1 is less than 0. That was the definition of decreasing. Okay, now what we're going to do is we're going to take a look at what is the mean value theorem. The mean value theorem says that f prime of c is going to be equal to f of x2 minus f of x1 over to x2 minus x1 for some c between x1 and x2. That is the mean value theorem almost exactly. Well, look at this. This numerator f of x1 minus f of x2 minus f of x1, that has to be less than 0, right? And then this denominator has to be greater than 0. That's what it says right here. So we have a negative on the numerator and a positive on the denominator. So what we've just shown is f prime of c is less than 0. Okay, we have a negative divided by a positive, so f prime of c is less than 0. So, really important, if a function is decreasing, that means its derivative is negative. Okay, we've shown that in a couple different ways now. So this next exercise asks us to prove that a function increases whenever its derivative is positive. Well, let's see. Okay, we're going to start off with f of x2 minus f of x1 is greater than 0. And why is that true? Well, that's the definition of increasing. And then now we're going to go ahead and we're going to say, well, if we take a look here, the next thing that we did was apply the mean value theorem. So we're just going to apply the mean value theorem. And then finally, we know that the numerator is positive, right? F of x2 is minus f of x1 is greater than 0 if you have a increasing function. This is positive up here. And then our denominator, f of x1 minus f of x2 minus x1, that's also positive. And so a positive divided by a positive is a positive result. So we've just shown that f prime of c is greater than 0. Okay. So what does this mean? This means positive derivative, functions increasing. Negative derivative, functions decreasing. I bet you already knew that, but now we've given it a little bit of a proof. So furthermore, a continuous and differentiable function is said to be constant if f of f prime is equal to 0 for all x. So if the derivative equals 0 for all values of x in the interval, then we have ourselves a constant function, which, you know, that looks like a horizontal line. Okay, so let's move forward and let's start talking about intervals of increasing and decreasing. So a task in calculus, common task, is to find and describe intervals where a function increases and decreases. So using the intermediate value theorem, we can see that continuous derivative must equal 0 if it changes. I'm not sure what the continuous is there for, but we can see that the derivative is equal to 0 if it changes from positive to negative. That doesn't really make a whole lot of sense, but basically what we're saying is that if a function, derivative is just a function, but if a function or derivative is going to equal 0, it has to be changed from positive to negative at some point, or maybe we should do the other way around. If a derivative changes from positive to negative, this is the way we want to say it. If a derivative changes from positive to negative, then the derivative has to equal 0 at some place. Same thing the other way around. If a derivative changes from negative to positive, then the derivative has to equal 0 at some point. Okay. Discontinuous derivatives also could change sign at a point of discontinuity. So that's something that could happen. Taken together, what this says, and this sounds like it's going to be the important part. So taken together, a derivative stays the same sign for all intervals that do not have a critical point. In other words, if a derivative is going to change signs either from positive to negative or from negative to positive, then it has to do so at a critical point. F prime is equal to 0 or undefined. Now the reverse of that isn't true. Okay, the reverse of that says that if f prime is equal to 0, that means that the derivative has to change from either positive to negative or negative to positive, which isn't true. That doesn't have to happen. But if a derivative does change from positive to negative or negative to positive, then it has to do that at a critical point. So now we have the derivative explicitly linked to the increase and decreasing of a function. So in order to find intervals of increase and decrease, we've just turned that task into an analysis of the derivative. Okay? By looking at the derivative, we can tell when a function increases and decreases and when it changes from increasing to decreasing or from decreasing to increasing. So number one, let's find all the derivatives and locate the critical points. We should actually read the problem. Describe all intervals where the function f of x equals 2x cubed minus 24x is increasing and decreasing. Okay. So the first thing we're going to do, locate all the derivatives and find the derivative and locate all critical points. So let's find the derivative. What is the derivative of 2x cubed? The derivative of 2x cubed is actually 6x squared. What is the derivative of 24x? That is just 24. Okay. So when is this derivative equal to 0? Okay, so you might want to solve that, but this is going to be equal to, this derivative is going to be equal to 0 when x equals 2 or x equals negative 2. Okay, so to solve that, you would just, of course, set the derivative equal to 0, and then you would just solve algebraically. So, second part of this, the part that a lot of students forget, is when is this derivative undefined? Well, this derivative doesn't have a denominator, so really it's never undefined. So what we're going to do is we're going to take the critical numbers and we're going to plot them over a number line. So let's see, on top of the number line, we're going to find negative 2 here, positive 2 here. We could probably put a 0 here just to make us feel like we have a center, although it's not really necessary. Okay. And then number 3, we're going to evaluate, or what I will eventually say is perform a sign analysis on the derivative for every interval by critical numbers. So what's the first interval? The first interval here is from negative infinity to negative 2. So what do we know about that interval? Well, that interval, we have ourselves f prime is positive. How can I tell? Well, let's pick a number here somewhere between negative 2 and negative infinity. And some of you might be thinking negative 3, but I find that my mental math works better if I just make it a really small negative number. It's like negative 100. Let's take negative 100 and square that. That gives us, I think, that gives us a positive 10,000. 6 times 10,000, that's 60,000. 60,000 minus 24, that is a positive number. Okay, so for all points between negative infinity and negative 2, the derivative is positive. Why is the derivative positive there? Well, we've shown that the derivative is positive at one point in that interval, and there are no other critical numbers in that interval. So then the derivative cannot possibly change sign in that interval if there are no critical points. What about the second interval, from negative 2 to positive 2? Now remember, negative 2 and positive 2 were our critical values. Okay, well, let's see. From negative 2 to positive 2, if I substitute a number in here, 0 is a good choice, actually. Not because it's in the middle, but because that's easy to evaluate mentally. If I substitute 0 here, I get 0 minus 24. So that is negative. Cool. And then the last one here, what about from 2 to positive infinity? Let's highlight that in green. from 2 to positive infinity, well, I'm going to have to evaluate that. And if I don't want to rely on the calculator, I better pick a number that's easy to evaluate. So a number that's easy to evaluate, let's say something like 100. Okay. 100 squared is 10,000. 6 times 10,000 is 60,000. 60,000 minus 24. If you actually subtracted that, you know you don't need to. So that's going to be a positive number. Okay. So those are our 3 intervals. Remember, since -2 and 2 are the only critical numbers, only critical values, there is no other place where the derivative can change from positive to negative or from negative to positive. Okay, so now that we've done that sign analysis, sometimes we don't like to write the word positive. We like to just put a plus sign. Sometimes we don't like to write a negative. We'll just use a negative sign, and that's perfectly fine. So we're going to use the language of mathematics and write this. The function f of x increases for the intervals of negative infinity to -2, union with +2 to positive infinity. And it decreases on the interval -2 to +2. Okay. This union sign right here just means that these two intervals are kind of belonging together in the same set, really. So be consistent with your written responses. Always use the language sentence starter above. So if this is a sentence starter that makes a lot of sense, it makes a lot of sense to me. So this is what you should be writing every time. Okay, and we're going to start incredibly with antiderivatives. So what is an antiderivative? Well, if one function is a derivative of another, then the functions are also antiderivatives. So let's say if f prime is equal to g, so the derivative of f is equal to g, that means f is the antiderivative of g. So let's take a look at this one. Since the derivative of x cubed is equal to 3x squared, the antiderivative of 3x squared is, well, that's x cubed. Okay, that's how they're linked, derivative and antiderivative. But is that the only antiderivative that exists for 3x squared? If I took the derivative of x cubed plus 1, isn't that always also going to be 3x squared? If I took the derivative of x cubed minus 1, isn't that also going to be 3x squared? So really, all of these are antiderivatives of 3x squared. So there isn't one single antiderivative for a function. There could be many of them. And in fact, there are infinite numbers of antiderivatives for a function. So because that's true, oftentimes we write a plus c at the end of this function, at the end of the antiderivative, just to show that it could be a whole bunch of different things. And the only thing different between them is a constant, like -1, +1, and 1/2. So for example, since the derivative of x cubed plus a constant is equal to 3x squared, the antiderivative of 3x squared is x cubed plus that constant. Okay, so what are some antiderivatives of 2x or 2x? Okay, well, how about this? Some antiderivatives of 2x. X squared definitely is 1. But what about x squared minus 8? Yeah, that's definitely also an antiderivative. And if you wanted to write this down, you would write that the antiderivative is x squared plus a constant c. What about for x to the 5th? What is the antiderivative of x to the 5th? Well, antiderivative of x to the 5th, you could say it's 1/6, x to the 6th power. And you can kind of mentally see how that works. But you could also do 1/6 x squared plus 13. And if you wanted to use that constant notation, the plus c notation, geez, my program's really giving me a hard time here. You could just write 1/6 x cubed, 1/6 x to the 6th power plus constant. How about the antiderivative of sine of x? Let's see. The derivative of cosine is negative sine. So then the antiderivative of sine, well, that can't be cosine. It's got to be negative cosine. So the antiderivative of sine x is negative cosine x plus constant. And then what about the antiderivative of sine? Well, the antiderivative of cosine. Well, the derivative of sine is cosine. So then that must mean that the antiderivative of cosine x is sine x. You could also write sine of x plus a constant, so you don't have to keep coming up with all the infinite number of things you can add to sine x for it to be the antiderivative. And look at that. That's really the end of this section. The key points here, you've got the mean value theorem. We have the definition of increasing and decreasing, and we mean the mathematical definitions of increasing and decreasing. And then we have intervals of decreasing are always separated by critical values, and you can use critical values and test points to find intervals of decreasing and decreasing. So we use the critical values to find the intervals. We use the test points to decide whether or not those intervals are decreasing or increasing. So let's finish things with our check your understanding. So we're going to find the average rate of change of y equals 2x to the 1/3 on the interval from -8 to 8. And thankfully, it gives me the formula for the average rate of change. Average rate of change is just the slope of the secant line. So then we're going to summarize the consequences of the mean value theorem on this interval. And then we're going to describe all intervals of increase and decrease on that interval -8 to 8. Well, first of all, let's find the average rate of change. The average rate of change here, in order to do that, we're going to have to find the derivative. That's not going to... No, I'm sorry. We don't need to find the derivative to find the average rate of change, but we are going to use that for the mean value theorem. So here's our derivative. The derivative of 2x to the 1/3 is 2 on top of 3x squared cubed. When is this equal to 0? Well, the numerator is never equal to 0, and that's kind of how I like to do this, of course. Look at the numerator, set it equal to 0. Doesn't happen. Look at the denominator, set it to 0. When is the denominator equal to 0? Well, that happens when x itself is equal to 0. So our only critical value is x equals 0, and that is of the undefined derivative, not the zero derivative variety. All right, so the next thing we're going to do, this one should be, we're going to find the slope of the secant line, which is the average rate of change. So the average rate of change, when I substitute +8, I get 2 multiplied by 8 to the 1/3 power. Okay, 8 to the 1/3 power is 2. And 2 times 2 is 4. Next thing we're going to do is we're going to find the function y evaluated at -8. So evaluated at -8, we get 2 multiplied by -8 to the 1/3 power. -8 to the 1/3 power is equal to -2. -2 times 2 is -4. So I believe this becomes 4 minus negative 4, which is, oh, that's 8. That's our numerator, it's 8. How about our denominator? That's going to be 8 minus negative 8, which is going to give us 16. So 8 over 16, that's equal to 1/2. So our average rate of change is 1/2. That takes care of this first part. Okay. We're going to need the mean value theorem. We're going to need our we're going to need our derivative and our critical value for intervals of increase and decrease, which we haven't got to yet. So let's go ahead and take our critical value, and we're going to plot that on our number line. There it is, right at 0. And then that gives us 2 intervals. This interval over here on the left, and this interval over here on the right. Okay, test points that you can use, negative 100 and positive 100. Actually, interesting. Negative, we only have to go from negative 8 to positive 8. So we really should find us a number between negative 8 and 0. And I think, if we use negative 1, that might work. Let's evaluate the derivative at negative 1. Okay, negative 1 squared is 1. Cube root of 1 is 1. 3 times 1 is 1. 2 over 3 times 1, that's a positive number. So our derivative is positive from negative infinity to 0. How about on the right side here? Let's pick a number on the right. I'm not so nervous anymore, so maybe let's pick 10. So 10 squared is 100. Cube root of 100 is positive. 3 times a positive is a positive. 2 divided by a positive number is also positive. So we have a derivative that goes from positive to positive. Well, look at that. Just because it's a critical number does not mean that it is that does not mean that the derivative is going to change sign. So, finally, we can go ahead and describe all intervals of increase and decrease. So, the function increases on the interval from negative infinity to 0, union with 0 to positive infinity, and does not decrease on any interval. Now, you might be saying, why can't I just use negative infinity to positive infinity? And actually, the answer is, do we know what's happening at x equals 0? At x equals 0, the derivative is undefined. Does that mean that the function's increasing? We really don't have any theorem for that. If the derivative is undefined, then of course it's neither increasing nor decreasing. Same thing is if the derivative is equal to 0, then the function is neither increasing nor decreasing. So we have to exclude them anytime we want to write them. You should not include a critical value in any interval if you're trying to figure out intervals of increase and decrease. Do not include any critical values. And that's it for us. We're definitely going to study more on these critical values, and thanks for coming along, and we'll see you next time here for more math lessons. Have a good one.